So I wanted to start with a thank you to the organizers of the conference and the workshop. It's been a truly stimulating program, and the connections between the far field and the near field have really been fantastic. So many thanks. Thank you also to Martin for his review of Lyman alpha absorption and emission this morning. That really set the stage. I want to focus on using Lyman alpha emission to learn about reionization, and in particular focus on some of the first large kind of ionized pockets, and using Lyman alpha in emission to pick out where those pockets are, and then in those environments studying what the ionizing sources are eventually. And if there's one thing that was a common theme in the other talks today, it's that using Lyman alpha in emitters to understand things quantitatively about reionization is hard. And I'm not going to argue with that, but I'm going to try to convince you that sometimes doing hard things is worth it, okay? And I'll point out, for example, I mean, we heard, right, that the discovery of just one Lyman alpha emitter at redshift 13 is already changing reionization models to start at earlier times. And prior to JWST, Lyman alpha emitters played a large role in establishing this protracted reionization history that's now been confirmed by many methods. So in modeling Lyman alpha emission from galaxies, the velocity offset of the observed Lyman alpha emission line is a big deal. It basically tells you how far away the neutral IGM around the source has to be, okay? So for a given distance, it gives you a minimum velocity offset. And to take that case in point, these are some models from Mason and Gronke and 2020. And what it shows here, for example, is as a function of the velocity offset from the line center of the Lyman alpha line, what the transmission is through the intergalactic medium as a function in color, okay, of the size of the ionized bubble. So like a takeaway point from this somewhat complicated graph with three different things plotted is that it's possible, in principle, to observe Lyman alpha emission from a galaxy in a completely neutral intergalactic medium. And you can see that here by the yellow line. If the line profile emergent from the interstellar medium of a galaxy is redshifted more than about 300 kilometers per second, okay, you can actually get substantial Lyman alpha transmission. This is at redshift 7, for example. So this is just one of the complications in interpreting Lyman alpha emission from reionization era galaxies is the ISM/CGM matters. Now in the JWST era, this is a summary from a recent paper by Joris Wittstock that combines 17 JADES galaxies and some other samples of Lyman alpha emitters from the other big surveys. And you can see in JADES alone, about half, okay, of those 17 galaxies based on their Lyman alpha velocity offsets seem to reside in large ionized bubbles. Okay, and these are bubbles with sizes of kind of 1/10 to 1 megaparsec in proper units. And interesting also is that about half of these Lyman alpha emitters seem to be associated with overdensities of galaxies. In these studies so far, attempts to look at how many ionizing photons are required to ionize the bubble compared to the galaxy populations seem to indicate that the Lyman alpha emitters are signpost of the galaxy overdensities, and that the galaxies actually providing the Lyman alpha, the ionizing photons, the Lyman continuum, are somewhat fainter than the Lyman alpha emitters being detected. But this is all still kind of up in the air, and I think ultimately what we're aiming to do with this kind of work is use the bubbles as a signpost, and then study the population of galaxies, AGN, in those bubbles to understand what's causing reionization. So today I'm going to tell you about our JWST observations of a particular large overdensity of Lyman alpha emitters at about the midpoint of cosmic reionization, when the IGM is roughly half neutral and half ionized. And I should draw attention to to Wei-da who discovered this object in narrowband imaging and gave a lightning talk the other day. He's also been responsible for a lot of the heavy lifting and the data reduction that we've done for this project, so a shout out to Wei-da. This is from his 2021 paper that shows a large region near the Cosmos field, but a patch somewhat outside the Cosmos Web Survey, where the number density of Lyman alpha emitters over here is about 5 times the average density. And if you were to kind of just estimate the sizes of the ionized bubbles based just solely on a very simple, estimate from the luminosity of the Lyman alpha emission and as an assumed escape fraction, you'd get a picture somewhat like this for 2 clumps of ionized bubbles around these individual Lyman alpha emitters that are overlapping to create this ionized pocket. And you can see here the rough sizes of these structures. And Wei-da estimated in this paper that these 2 sub-protoclusters would eventually merge into one extremely massive structure. So let's take a look at some of the data. Okay, to compute these velocity offsets, we first need Lyman alpha spectra. Okay, these are from the ground, from Keck and the LRES spectrograph. And you can see here many of them show kind of the classic Lyman alpha profile of a central peak and then a red wing where there's been multiple scatterings. Okay. So the aim here is that we measure a redshift from the Lyman alpha emission, and we want to compare this to the H alpha emission, okay, the Balmer emission that we'll observe with JWST, to get the velocity offset of this Lyman alpha emission relative to the redshift set by the optical lines. In principle, we also want to compare the luminosities, okay, in Lyman alpha to the Balmer line luminosities to learn about escape fractions and transmission. So here are JWST NIRSpec spectra of a sample of our objects. We have 10 in total, okay, so this is almost all of them. And you can see, surprise, surprise, many of these have spatially extended, okay, optical line emission along the slit. This is because they're clumpy galaxies composed of multiple parts. I'll show you some images later. Many of them have broad components, but not terribly broad, the sort of broadness of a few hundred kilometers per second that we typically see in galactic winds. So in these objects, we use the H alpha to measure a redshift, and we very robustly, okay, calculate then the offset of the Lyman alpha emission, which is always redshifted compared to the Balmer emission. So that's shown on the x-axis here. And the x-axis we're very confident about. Typical velocity shifts here are quite small by Lyman alpha standards, okay, just 100 to 150 kilometers per second, indicating that these galaxies must lie in a large ionized structure in order for us to see the Lyman alpha. There's a couple of them that have larger shifts of 200 to 250. Okay, on the y-axis, this is marked preliminary for a reason. We're still debating about it within our own team of exactly what the ratio of the Lyman alpha emission to the H alpha emission is here. But these are some preliminary numbers where here we've kind of ignored the attenuation of the ISM as a starting point. And in that scenario, you can see here that typical escape fractions would be like 40 to 60% for the Lyman alpha emission, which for those of you who work on similar things, those are very large Lyman alpha escape fractions. As I said, these are preliminary numbers where the ISM attenuation is not included yet. We'll talk about that briefly in a minute. But if I translate this into the sort of model that I discussed in the prior slide, you can see that this would correspond to bubble radii of kind of 0.5 megaparsec up to almost 2 megaparsecs. Okay, so we will need to account for the attenuation of the ISM, which is admittedly a hard problem, but I want to argue that it's one that I think we can solve with some work because of all the information that's in the rest frame optical spectra that JWST provides. So here are 3 plots, work done by Wan Yang some years ago, using green pea galaxies, okay? So using galaxies in the local universe to learn about the physics of the ISM and establish empirical correlations between the Lyman alpha escape fraction and different properties, okay? The width of the red peak of the Lyman alpha profile, this velocity offset that I was just talking about, and the dust content, okay? So you see correlations with each of these quantities. Why? Because Lyman alpha escape fraction depends on the H1 column density, it depends on the dust, and I say dot, dot, dot because it probably depends on a number of other things, like the covering factor, okay, and perhaps the star formation history. But this is an empirically derived relation for the Lyman alpha escape fraction from the ISM, that what we're doing is using that because we can measure the red peak velocity shift. We can measure the dust reddening from the Balmer decrement and claim that we know this for an individual galaxy. So then our IGM transmission, the idea is to map that along the sight lines across to each Lyman alpha emitter in the protocluster. So instead of comparing the observed Lyman alpha emission to the intrinsic Lyman alpha emission, okay, 8.7 times the H alpha luminosity, we can correct that intrinsic emission for the escape fraction from the ISM, is the idea here, okay? And that is work in progress, but I want to argue kind of where we can go from there. So we want to use the sizes of these ionized bubbles then to get an idea of what the ionization rate, okay, of the IGM was. And here's an equation from Sen and Hyman describing the propagation of the ionization front, okay, and following other work at these redshifts, the term from the Hubble expansion and the recombination rate are not dominant, so ignoring them, right, we can solve that equation for the ionization rate, okay, in terms of basically a volume that's been ionized, one ionizing photon per hydrogen atom, divided by a time scale, where that time scale is related to the length, okay, of the starburst in the Lyman alpha emitter. Okay, but let's take that a step further, right? Let's suppose that these ionizing photons come from the galaxies or the Lyman alpha emitter that we see there, okay? The galaxies, we now have an idea of how many ionizing photons they produce because the ones that didn't escape from the galaxy are the source of the Balmer alpha emission that we see in the optical spectrum. So in other words, we've got an ionization rate of the IGM that's equal to the production rate of ionizing photons by the stars times their escape, times the Lyman continuum escape fraction, maybe some picture like this. But that rate of production of ionizing photons, we can calculate from the H alpha luminosity if we account for the fact that only the photons that didn't escape are absorbed. So putting those two equations together, we can basically work out for a given Lyman continuum escape fraction, how long would the starburst have to last to make these two things balance, okay, to make all the ionizing photons come from the galaxy. And this is something that's still work in progress that we're working on for the different escape fractions and the different bubble sizes. But we're getting some reasonable timescales here. Okay, you have 100 million years for a bubble of half a megaparsecond size, which kind of leads us to think that the Lyman alpha emitters that we see could actually be, and I say could because this is work in progress, but could actually be providing a significant fraction of the photons required to ionize the bubble. So I'll finish up here just by pointing to the morphology, okay, of these Lyman alpha emitters. There's two examples here where this is rest near UV picture. This is rest optical spectrum picture. The rest optical contains strong H beta in O3, so think of it as an emission line object. So these are clumpy galaxies, and 85% of them are clumpy. The blue circle up here shows that if these were all mergers, in the sense of galaxy-galaxy mergers, that would be a much higher merger fraction than dark matter simulations predict. Only about half of them should be. So probably they're clumpy, but that they're not all mergers. They're more like this picture of filaments, okay? And filaments creating clumps. And in future work, we'll be using the spatial extent of this emission along our NIRSPEC slit. So we're basically measuring relative velocities of these clumps, where in some cases they're more or less the same velocity, and in other systems there's a significant Doppler shift between them. And I'll just leave my conclusions up before Andrea chases me away here. Thank you.
Thank you very much. Thank you very much. We have time for at least 2 or 3 questions. So, yeah, there's one.
Thanks, Crystal. That was great. I want to make sure that I understand the slide that where you had I think you're predicting F-escape Lyman alpha as a function of EB minus V and Lyman alpha kinematics. And that folds into, okay, the observer. Okay, so I guess my question is, it seems like there's a lot of scatter in these relationships that will translate into a pretty large scatter in your, intrinsic Lyman alpha escape fraction. So I was wondering, looks like there's like sort of a factor of 10 uncertainty at any value of those things. So I was wondering, does it still give you meaningful constraints given that?
Absolutely. I mean, it gives gross constraints, right, at this part. And, who's to say, right, whether the structure of the ISM that's embedded in this empirical calibration has anything to do with the structure of the ISM at high redshift, okay? Admittedly, it's a starting point. And I would actually argue if I'd had a bit more time, the key, I think, to the escape is like the star formation history of these clumps. And we have a paper on a couple local galaxies that you can take a look at where it very clearly shows that like the propagation of the starburst is what determines the Lyman continuum escape. There's a timing problem, right? That you need a wind from older stars, from a previous clump, to make the hole that the young photons from the youngest clump go out of. So I think those empirical relations are wonderful because they're a starting point, but by no means the answer to a very complicated question.
Thanks.
Yes.
More questions? We'll take Brent question down there.
Thanks. Can you go back to the equation where you infer the length of the starburst? So in this equation, if F-escape is low, does that approach like the age of the universe or exceed the recombination time?
Well, sure. If there's no escaping radiation from the galaxy, then it would take an infinite time to ionize the bubble.
Yeah, I guess I was trying to be a little bit more subtle than that.
Yeah.
Do you have a sense of whether you can actually infer a constraint on F-escape just based on the idea that there's some minimum time scale for a starburst and you see some H2 region of a given?
You kind of play the game either way, right? You can think you know something about F-escape or say it's a half, right? So that term is 1. And learn something about T star, or if you have equivalent widths of the emission lines and potentially Balmer absorption or something that would let you measure an age definitively, or good SED fitting, you could claim to learn something about F-escape, I think.
Okay, thank you.
Well, I also connected to that, to the previous formula. Actually, if you go to the previous slide where you have the log of F-escape formula, no, not this one. Log F alpha. Log F alpha. And the correlation. Yeah, this one. So if I have E equal to 0 and V equal to 0, I get the maximum value for 0.46. So where does it come from?
It's coming from the intercept, right, of the least obscured.
Yeah, but physically, I mean, why should... I'm trying to understand what happens if you have no outflow and 0 EB minus V. So well, what is the meaning of the formula? Maybe we can discuss later.
I mean, it's an empirical relation physically. I
Sure.
assume it's the H1 in the galaxy. There's still neutral hydrogen in the galaxy, even if you have no dust.
Yeah, but it's a constant. Okay, we can discuss.
Yeah, let's talk about it.
I think it's similar, but so then I'm trying to square the Lyman alpha emitters creating the bubble with, I guess, the conventional wisdom, which is that we have to go to much fainter galaxies to produce enough ionizing photons to reionize the universe or anything. So, but maybe the answer is that, you know, these are really beefy Lyman alpha emitters, and we know that Lyman alpha escape is correlated with Lyman continuum escape. So I just wanted to know if you wanted to comment on that or square that up.
I would start with a cautionary remark that I am not claiming at this time that the Lyman alpha emitter provides all the ionizing photons. As a preliminary result, I'm saying I was surprised to see an indication that it might provide a big chunk of what's needed, because I expected it to be lower luminosity things, okay, in the region. And then speculating about why they might be high escape fraction objects is just the star formation history, and that they are so clumpy, and this could contribute to making holes. Okay.
Okay, well, we have to move on. Thank you very much, Crystal. And